Imagine waking up one day to the sudden realization that the sky above you is nothing but a rendered skybox.
Here are 12 reasons why reality might be a simulation. Number 12. What happens if it ends?
When humanity contemplates the end of the world, we visualize fire and kinetic force.
We picture a rogue asteroid turning the atmosphere to glass. We imagine the sun swelling into a red giant and swallowing the inner planets. Or we look billions of years into the future toward the slow, freezing heat death of the cosmos.
These apocalypses have one thing in common. They obey the physical laws of the universe.
They tow time, they leave behind ruins. But a simulated reality does not die a physical death. It suffers a termination of execution. Look at how we build and manage software. Every program, no matter how complex, runs because it is allocated memory and processing power by a host machine.
It runs to fulfill a function, whether that is crunching variables for a climate model or providing a sandbox environment for digital agents.
The moment the data is collected, or the moment the host needs those resources for a more important task, the program is closed.
If we are living inside a digital architecture, the end of our universe does not require a cataclysm.
It requires a single keystroke, a decision made by an administrator sitting outside our dimensions.
There would be no warning sirens. The stars wouldn't flicker out one by one.
Our sun wouldn't explode.
The execution of our reality would simply be paused and then terminated.
1 millisecond, the universe is expanding, galaxies are spinning, and humans are breathing.
The next, the render stops. It wouldn't even fade to black, because darkness is a physical state that requires space and time to exist.
The end of a simulation is the sudden, permanent absence of all things. The plug is pulled, the memory cache is cleared, and we cease to be.
Number 11. Nested simulations.
Think about the trajectory of our own civilization.
A few decades ago, our most advanced simulations were pixelated dots moving across a black screen.
Ooh, eureka! It works! The theory holds.
Today, we run massive procedurally generated universes in our video games.
And we use supercomputers to simulate the collision of galaxies and the folding of proteins. Our processing power grows exponentially. Eventually, we will build a machine capable of simulating a universe down to the atomic level.
Populated by artificial intelligences that possess consciousness.
Those digital beings will look around their rendered world, study its physics, and eventually build their own computers.
Then, they will simulate a universe of their own.
The beings inside that simulation will do the exact same thing. This creates a cascade, an infinite regression of realities. A stack of Russian nesting dolls stretching down into digital oblivion.
Now, apply cold probability to this scenario.
If it is possible for a universe to spawn simulations, and those simulations spawn more simulations.
You end up with one base reality and billions of artificial ones.
If you were to pick a universe at random out of that stack, the mathematical odds of picking the single original biological universe are practically zero.
You are forced to confront the math. We are not base reality.
Wait! The numbers! It's all true! And gasp! We're not real!
The universe we live in is likely layers deep within a cosmic mainframe. A simulation running inside a simulation, running inside a simulation. The physical matter you touch is just inherited code.
Completely isolated from the true, original universe where the first machine was built.
Number 10. Who are the simulators?
We have a habit of projecting our own emotional needs onto the concept of a creator. When we theorize about the beings running our simulation, we want them to be enlightened.
We imagine post-human scientists studying their ancestry, or benevolent alien philosophers guiding our evolution. We want to believe that whoever built this universe cares about the people inside it.
The architecture of a simulation suggests otherwise.
The host running our universe might not be biological. It might not possess empathy.
Our entire cosmos could be the byproduct of a cold, indifferent artificial intelligence. A supercomputer tasked with mapping out cosmic variables or testing a specific logistical equation.
In this scenario, we are not the point of the simulation.
We are just a side effect of the chemistry engine. Alternatively, the creator might be an ordinary entity in a higher dimension. A bored East Asian male adolescent running a standard universe generation software on a consumer-grade quantum console. To them, the entirety of human history, the rise and fall of empires, the invention of art, the collective suffering of billions of conscious minds might just be a fleeting background process. A 5-minute distraction before they turn off the console and walk away. They do not hear our prayers. They are not waiting to judge our morality.
We are exhaust!
If a specific galaxy cluster begins taking up too much processing power, or if the parameters of the test drift too far from the baseline, an automated maintenance script could quietly patch our solar system out of the code to save memory. Number 9. The fine-tuning problem. Cosmology has a deeply uncomfortable secret. The universe is entirely too perfect. The fundamental forces that govern everything around us.
Gravity, electromagnetism, the strong and weak nuclear forces.
Operate according to specific numerical values. These are the constants of physics.
If you alter any of these numbers by even a microscopic fraction, the entire architecture of the cosmos collapses.
If the strong nuclear force, which holds atoms together, were just a tiny bit stronger, stars would burn through their fuel in a matter of seconds, making life impossible.
If gravity were slightly weaker, the matter from the Big Bang would have dispersed so quickly
that galaxies could never have formed.
If the mass of an electron were tweaked by a fraction of a percent, complex chemistry could not exist.
Physicists call this the fine-tuning problem.
The universe sits balanced on a razor's edge. It looks undeniably rigged.
While some scientists use the multiverse theory to explain this away, claiming there are infinite universes with random rules, and we just live in the one that worked.
The simulation hypothesis provides a much cleaner, more clinical answer. The numbers are perfect because they were typed in.
When a programmer creates a digital environment, they establish the physics engine first.
They set the gravity. They define how light behaves. Our universe is not a chaotic, random accident that got lucky.
It is a highly controlled sandbox.
The physical constants are parameters specifically calibrated to ensure the environment remains stable long enough to generate conscious observers.
The math doesn't lie. The universe was configured.
Number 8. Glitches in reality.
No software is flawless, no matter how advanced the hardware or how elegant the code.
Any sufficiently complex system will eventually experience rendering errors.
Memory degrades, variables conflict, the engine struggles to process conflicting data.
The fabric of reality. It's full of bugs. Glowing red bugs. Oh my.
If our universe is a digital construct, we should be able to look closely at the fabric of space-time and find the bugs.
We see phenomena that defy every natural model we have ever constructed. Look deep into the cosmos at the Bode void. It is a spherical expanse of empty space, nearly 330 million light-years across.
According to our models of how galaxies form and cluster, a void of this magnitude shouldn't exist.
There hasn't been enough time since the Big Bang for an empty space that large to clear out naturally.
It looks like a massive, unrendered chunk of the map, a dead zone in the server.
Then there is the dark flow.
Look! The galaxies, they're all moving together. Wait, what? This is huge! The whole sky is flowing!
Astronomers have observed hundreds of galaxy clusters moving in a specific, unified direction at millions of miles per hour.
Pulled by something completely outside the observable universe. It breaks the fundamental assumption that the universe expands uniformly in all directions. It acts like an error in the physics engine, a directional glitch, dragging physical assets toward an unallocated coordinate.
On a smaller scale, human consciousness routinely experiences anomalies.
The Mandela effect, where vast groups of people share identical memories of historical events that never happened.
It's just confirmation bias, misremembering, and psychological suggestion. Collective false memory, not shifting timelines.
But viewed through the lens of a simulation, it resembles a sloppy data overwrite.
The administrators patched the timeline, altered a historical variable,
but failed to wipe the local memory caches of all the connected nodes.
The glitch remains in our minds. Number 7. The observer effect.
At the microscopic level,
reality behaves in a way that shatters our common sense.
It centers around a principle called the observer effect.
Most famously demonstrated by the double-slit experiment.
When physicists fire individual particles, like electrons, toward a barrier with two tiny slits, they expect them to act like physical bullets. Instead, the particles act like a wave, passing through both slits simultaneously,
And creating an interference pattern on the detector screen behind them.
They exist in a state of superposition. They are not in one specific place. They exist as a cloud of mathematical probabilities.
Aha! It's a particle! I measured it!
But the moment a scientist places a measuring device next to the slits to observe which path the electron actually takes, the wave function collapses. The electron stops acting like a wave and behaves like a solid, localized particle, passing through only a single slit. Reality literally changes its physical behavior based on whether or not it is being watched.
In the physical world, this makes no sense.
But in computer science, it is the most basic principle of rendering optimization.
If you are playing an open-world video game, the processor does not render the entire planet at once.
It only renders the environment currently visible to the player's camera. The world behind the player doesn't exist as solid geometry. It remains suspended in the code as dormant data, waiting to be called upon. The double-slit experiment is the universe doing exactly this. It proves that the cosmos does not render the microscopic world until a conscious observer demands the data. The particles remain suspended in probability to save computational bandwidth. The universe doesn't exist when you aren't looking at it.
Number 6. Quantum indeterminacy.
This fundamental law of quantum mechanics states that you cannot simultaneously know both the exact position and the exact momentum of a particle.
The more precisely you pin down where an electron is, the less you can possibly know about how fast it is moving.
For a long time, scientists assumed our tools were simply too clumsy. We thought the act of measuring the particle bumped it, changing its trajectory.
But modern quantum physics has proven that the fuzziness is built into the universe itself. The particle actually does not possess a defined position and a defined momentum at the same time.
If we live in a simulation, this isn't a mystery. It is a hardware limitation.
Think about the computational load required to run a universe.
You have to track the position, speed, spin, and mass of every single subatomic particle.
A computer with infinite memory might be able to do this.
But a computer with finite resources has to make compromises. It has to compress the data.
Quantum indeterminacy is the compression algorithm of our reality.
Just like zooming too far into a digital photograph reveals blurred, pixelated artifacts.
Probing too deeply into the fabric of matter reveals the processing limits of the host machine.
The engine simply cannot afford to assign a precise location and a precise speed to every particle simultaneously.
So it blurs the details at the bottom of the map.
Number 5. Planck scale pixelation. We experience space and time as a continuous analog flow.
If you move your hand from left to right, it smoothly glides across the empty air. You can divide that distance in half, and in half again, down to infinity.
That is how the human brain processes movement.
But physics tells a completely different story. Space and time are not continuous. They are digital.
Welcome to the Planck scale.
The Planck length is the smallest measurable unit of space in the universe.
Measuring roughly 1.6 by 10 to the -35 meters.
According to the foundational math of our reality, distance smaller than the Planck length does not exist.